Okay. Gravitational potential energy. Example 2. This one is about what happens when you have several masses acting together. We will kind of be building on this idea in the next unit. But here's the question for now. A square of side length A is formed by bringing 4 masses, each of mass m, from infinity. What is the total potential energy of such a distribution? So we are trying to construct a shape that would look something a bit like this. Along each side is a distance a. At each point there is a mass m. And we want to know what is the total change in potential energy associated with that. In this case, since we're bringing things in from infinity, we can think about it as just being u and not delta u, because u at infinity is 0, so it won't count for anything. All right. To point out, the equation for potential energy minus big G mass 1 mass 2 over r. This goes to 0 at infinity is one of the big things about it. But it involves 2 masses. If you only have a single mass, you have no potential energy. So here's how we're going to think about this. We bring a mass in from infinity, and we drop it off at its final location. U is undefined, really. There's no potential energy associated with this motion because there's nothing it's interacting with. So first step is pretty boring. Second step gets a bit more interesting. We take a mass somewhere far away and we bring it in to its final location, which is going to be a distance a away from our first mass. Now that has a potential energy associated with it. We started out with none because they were infinitely far away. And then now that we've brought it in, we now have a potential energy, and we know exactly what that is. It's going to be minus gm squared, because they're the same mass, divided by the distance between them, a. So we're going to call this U12. It's the energy associated with that interaction between mass 1 and mass 2. All right, now that situation already exists. We're going to take another mass out here at infinity, and we're going to bring it in to a location that is also a distance away from mass 1. Okay, and we're going to think about what's the potential energy associated with bringing it in, just considering mass 1. Well, the interaction between mass 1 and mass 3 looks pretty much the same as the interaction from 1 and 2 before. But now we've got something else going on. Notice there is also an interaction across the diagonal. Now think about what's the distance across the diagonal. If it's a on one side, a on the other side, you can use Pythagorean theorem to figure it out. This distance across the middle will be square root 2 of a. So that means there's also a potential energy between 2 and 3 that looks like minus gm squared over square root 2a. All right, we're going to finish this off by taking our fourth mass. This one was bringing in number 3. And here we are way out at infinity, and we bring it in to a point that is a away from mass 3, a away from mass 2, and across the diagonal, it's going to be square root 2a again. So for that, we're going to get, for mass number 4, a u between 1 and 4, which will be minus gm squared over, that's across the diagonal, square root 2a. Then we're going to get another one between 2 and 4, and that one will be equal to minus gm squared over a. And then, let's see, we've got one more between 3 and 4, and that'll be another gm squared over a. If you sum all the individual u's, you get the total for the system. Now I'm going to look at this and simplify things down. I'm going to mark ones that are the same type in blue. So this U12, U13, they are exactly the same. U24, whoops, the infinity isn't part of this. U24 and U34 are also the same thing. Then here in pink, we've got two types that depend on that diagonal distance. So in the end, here's what we get. U for the whole system is 4 times minus gm squared over a plus 2 times minus gm squared over square root 2a. And if you want to, you can try and clean this up. It doesn't clean up beautifully, I have to admit. So we could pull the minus gm squared over a out in front, and that's going to leave us with 4 plus 2 over square root 2. And again, that 2 over square root 2, you could clean that up a little bit if you wanted to. You could get the square root off the bottom, then you'd have 2 square root 2 over 2, which would basically be, what is that, square root 2? How entertaining. Let me see. Can we do that with just the one side? Yeah, we can. So yeah, you can play around with this a little bit, but this is pretty much what we're looking at for the answer. Now, why did I even bring it up? You do the same problem but with an equilateral triangle on your homework. You do kind of have to know how to deal with multiple particles in the system, but we're fortunate it's just a simple sum. All right, so we're going to stop the second example there, and I'll see you in the next set of videos.